Okay, Ji. So slides are visible, and I am audible, right?
Yes, sir.
ठीक है जी. Thank you.
जी sir.
अच्छा जी. So right जी. So let's switch back to English and let's start um, our uh, our discussion formally for today. I was giving a brief recap of yesterday's lecture, and we we discussed delay and losses. In particular, we spent a fair amount of time on discussing delays, and we discussed the four components of delays: transmission, propagation, um, queuing, and processing delay. Processing delay is usually negligible. Queuing delay, it is hard to quantify it, but we tried to quantify queuing delay with the help of with the help of this very important parameter, which is called traffic intensity, denoted by LA by R. So LA is the incoming rate because it's L, which is bits, the length of the packet in bits, and A, which is the arrival rate of packet. So LA, the product of LA is an incoming rate, and R divided by R, which is actually the outgoing rate, the rate to which the device is attached with. And obviously it's a unitless quantity, bit per second divided by bit per second, and the value will hover around from 0 to 1. And we discussed in yesterday's class that if we have uh, if we have so yes, I need mouse. Okay, if we have something over this area, some value of traffic intensity close to this area, then we have I mean, we are in the queuing delay portion, which is fine. And if we are moving towards 1, then this will lead to a large queuing delay. And example as well, if you remember, in which I said that, okay, if the packet per second is if A is 5 packet per second, and second for a single packet, then the incoming rate and outgoing rate will basically be equal. So 5 packets are arriving to the router in 1 second, and 5 packets are departing. Then why there will be a queue being formed? And then we discuss that it will depend on the nature of arriving traffic. Okay, so the nature of arriving traffic, if it is in very properly spaced with equal size intervals of L by R, then there will be absolutely no queue. Okay, but that's generally don't happen in the packet switch network, and we have traffic arriving in bursts. So over a larger period of time, we will have queuing delay. After that, we discussed end-to-end delay, and then we saw with the help of traceroute uh, how how a real end-to-end delay will look like over the internet, right? And this was the traceroute from University of Massachusetts in US to a research institute, Eurocom, in France. And we saw in traceroute, it depicts a very interesting information, not only for the entire path, but also the values of different probes being sent to node 1 to up to so on to node n, where n being the destination node. Okay, and we also did some traceroute ourselves to my parent university, www.puntopolito.it. Okay, and if we say it in Italian, when that university, since it was blocking the ICMP messages, there was no reply, and to Google and something like that. I hope some of you must have played with this utility at your own. It's a good one. So you can see the whole path over here, which network you are entering, and things like that. Okay, here you can see the names of the router and the network. So from here onward, we will continue. This again is the continuation of our delay, the topic of delay, and a very good and very important slide. We'll discuss this slide. Let's just wait a minute for the Maghrib Azan. Okay, it's I'm finding it a bit how do you say, weird to keep talking, and there is Azan noise at the background. So let's just Wait few seconds. Okay, what is being presented here in this slide, we can see that there is this is a you can see this is on the y-axis. So the way to read a graph obviously is that you will see what is being plotted at the x-axis and what is being plotted at the y-axis. So at the y-axis you can see that we have the CDF, the cumulative distributive function in percentage at the y-axis, and on the x-axis we have the round trip time in millisecond. Okay, so the time in trace route or in ping, what you report actually in those ICMP messages is the RTT. The value of RTT is being reported over here. So when you send a probe or you send a ping, both are ICMP messages. Ping and trace route both are ICMP messages. When you send those messages, the source at the time of sending, start a clock, and then the message reach to the intended node, which is in the case of ping is the final destination. In the case of trace route, it's the first, second, third, and up to all the nodes. Whatever is the destination node, it will return the reply, and then the time will be recorded. This is the RTT, obviously we know. So the value of RTT is here on the x-axis, and the CDF, the cumulative distributive function, is on the y-axis, and we have two curves. The first curve is for Stanford, Princeton, which is the green one over here. Okay, this one. And the second curve is between Stanford and Tsinghua. Okay, all three are the universities: Stanford University, Princeton University, and Tsinghua University. Okay, the curve between Stanford and Princeton is these are the two universities on the east and west coast of United States, right? Stanford is on the west coast, and Princeton is on the east coast of United States. There is a distance of 4,000 kilometers. Okay, and we can see in the curve that we start at the value of 100 millisecond of RTT. Okay, we start at the value of 100 millisecond. Okay, right here, and we see that almost 60% of the time or 70% of the time our experiment result in this value. So CDF is basically a cumulative distributive function, which is saying that, okay, if you did a trace route experiment or a ping experiment, let's say 1,000 times or 10,000 times, how much cumulative distributive function is telling you the frequency of any part of occurrence of any particular result. So it is basically telling you that 60% of the time we have a result which is around this value of 100 millisecond. Okay, and then there is a variation. Sometimes we ran the experiment, we did ping or we did the trace route, and the final answer from Princeton actually came with a slight variation. So I mean the total variation we have is approximately 50 millisecond. So we have all the results, the 100% of the results. I mean, if we did 1,000 times ping, all 1,000 pings values are resulted between 100 and 150 millisecond, somewhere around. Okay, so if and similarly the second curve, you can read it yourself, that obviously Tsinghua is a university in China, so the distance is huge. Okay, you can see that there is a 10,000 kilometer distance, and the variation is 200 milliseconds. So some very important outcomes or takeaway messages. Okay, when you are reading the graph, one thing is that you did some commentary on the graph. So the commentary is that what is x-axis, what is y-axis, and what are the curves showing, and then you delve deep into the graph, the why. You start explaining the why. So now I'm going to ask you this, that why the minimum value of Stanford Tsinghua graph is 330 millisecond, and the minimum value of Stanford Princeton graph is 100 millisecond and not below that. What is the reason that there is no value below this certain value. For example, in the case of Stanford Princeton, there is no experiment resulted in less than 100 milliseconds. So no ping or no trace route resulted in less than 100 milliseconds. So that means that this is a hard bottleneck. This is a hard value of delay which we cannot beat. So how I want to ask, in your opinion, which component of the delay is driving this value? Propagation delay, which we cannot beat. If there is a certain distance, we have to cover that, and there's a certain speed, d by s. The answer is the propagation delay, and this is the component of the delay which will give you a constant, a minimum limit, a hard bottleneck. That is the value which you will never be able to beat between a particular source destination pair. And similarly, because the distance is more, the d is more, d by s, the answer will be a bit more over here. Okay, so 330, we cannot do better than that. Even if we have zero queuing delay. And then there is a variation. There is a variation of 50 millisecond in Stanford Princeton graph, and there is a variation of 200 millisecond in Stanford Tsinghua. Which component of the delay is driving this variation? It's the queuing delay. Okay, so the queuing delay is mainly the component which obviously depends on the level of congestion, and on because the congestion is something that changes at each and every particular instance of time. That's why depending upon that, we will have this particular variation. So the same experiment between same pair of nodes may result in a different value of ping or trace route, whatever we are having, of delay. Okay, and obviously why delay is less over here and delay is more over here, you guys know that this is a much longer path, and the probability of having variation in queuing delay over a much longer path is more as compared to the probability of having variation in queuing delay over a shorter path. You're following it, right? You're getting what I'm talking about, right? And another reason apart from queuing delay, which is not a very common reason, is also that the packets, this is not a circuit switch network, it's a packet switch network. From now onward, we are discussing internet, and internet is a perfect example of a packet switch network, and packets may take different paths as well. So each and every path may add a slight variation between the same source destination pair. Okay. So if you notice, first we discuss the components of the delay, then we discuss nodal delay, and then we discuss trace route end-to-end delay, and now we discussed a large representation of many values of end-to-end delays. Okay, so we had a very detailed and very how do you say? I mean, a complete discussion on internet delays, and it is important. This topic is important. It is concluded over here. Next, which was left in yesterday's slide, was throughput. It's just very simple. I will just give you one. I will just show you guys one figure, and we will discuss throughput with the help of this example of fluid dynamics. Okay. So I will say say a sentence, and that sentence is the takeaway message of the throughput thing. It's not that longer topic, just like delays. So we don't have many things to cover. The throughput between any source destination pair is always constrained by the bottleneck link. So which means if in this figure you notice that if you start pouring water from the top, okay, from the source, which is this tap, and you keep pouring water, the amount of water which will be passed from here will always be constrained by this particular section of the pipe. Okay, you guys agree, right? I mean, you keep pouring water from the source over here, but it may happen that water starts spilling out from the vessel at this point. But if the ingress rate is too much, but the egress rate from over here towards the destination, towards the receiver, will always be constrained by this bottleneck link. Okay, the bottleneck link is the one which is having the lowest capacity. So in terms of networking, if we say this, if we take this scenario, for example, or let's go upward in the trace route. So for example, if you notice, there are 19 intermediate nodes, and on the 19th hop we reach our destination, which is Eurocom.France. Okay. So what will be the throughput of this particular connections between source umass.edu and destination Eurocom.fr? It will be constrained by the bottleneck link. So which of these link is offering the minimum bandwidth to this connection? Okay. In another example, which is shown over here, you can see that there are many servers and there are many clients, and an internet cloud is shown over here. So we may have, you know, many nodes, intermediate nodes. We are not interested, but let's assume that there is one link of R. Okay, it's this one is in the core of the network, so it may be a very high bandwidth link, and we have all the servers connected with RS, you know, the rate of the server, and all the clients connected with RC, the rate of the client. So what will be the end-to-end throughput between each connection of client and server? It will be minimum between RC, RS, and R by 10, because this R is divided among 10 connections. So RC. So if we just take an example of one pair, that pair is between this RC and this RS. So this client server pair over here. So the connection is passing through three links: RC, R, but it is getting a portion of R by 10, okay, and RS. So which of these three is minimum? That will be the bottleneck link, and that bottleneck link will derive your throughput, okay. And by the way, this throughput is the value which we guys are really interested in. So whenever you start downloading a file on internet, you know, there is a value on the top right or top left of your browser, which is showing the instantaneous throughput of that file being downloaded, and you guys keep a very close eye on that value, you know, most of the time. So when the value keeps rising, you know, our happiness keeps rising, and when the value is dropping, we are becoming sad because the internet connection is not downloading our movie very quickly, right? Actually, so that's the only takeaway message. It's written right here. You can see link on end-to-end path that constrain end-to-end throughput. That is the bottleneck link, okay? And the bottleneck link is the one which derives the overall throughput of the end-to-end connection, okay? We conclude our lecture, yesterday's lecture over here, and let's continue our discussion. And let's have I will skip through some slides because I do not intend to spend any more time on the first chapter of introduction of Cross and Rossbook, right? So in the remaining time, I will skip through some slides. I will just touch the important slides. Okay, do not worry, the recordings are there, and only the slides that I touch will be included as part of your curriculum. So don't worry, because I know that this is very important for you guys to understand that all the slides uploaded on LMS will be part of curriculum. No, the slides that I will touch right here will be part of your curriculum. Okay, I will touch only important slides because from next week I would like to discuss DNS, HTTP, and then transport, and then the main content, which is the switching and routing. So I mean, in let's say 4 or 5 weeks time, I would like to have everyone on the same page of networking knowledge. So again, I will say for some of you it may be a quick and brief recap, but for some of you, for the others of you, it is something new and an addition to your knowledge. Okay, so please don't mind if I'm skipping through some slides in this particular lecture which I'm about to deliver right now. So in front of you, internet structure. Internet itself is a network of networks. It's an interconnection of many small networks. You know, many hundred thousands of even millions of small networks. You know, and each small network is being governed by a certain autonomous body. Okay, which and that is why when we will study the routing portion of the course, we will call those networks as autonomous systems. If you guys have heard about this term, in particular the BGP, the Border Gateway Routing Protocol, called. So for example, PTCL, the whole network of PTCL for the global internet, it's an autonomous system being run and governed by PTCL. Okay, and the whole network of Nayatel, all the routers including in that network, is a separate autonomous system. And then there has to be a peering point where these autonomous systems meet each other, you know, link to each other, and then there has to be a peering point or a gateway point for the whole country. Okay, and similarly up to so on, so that the global internet stays connected. Okay, so so that's what we are going to take a stepwise approach to describe the current internet structure, which is a network of many networks. Okay, so we have a question. We have given million of we are given million of access ISPs around the world. Okay, so there are access ISPs in Pakistan, in Australia, in New Zealand, in California, and everywhere around the world. Okay, all of these access ISPs are separate autonomous bodies, separate autonomous networks. So there is an access ISP over here, which is being governed by NATEL. Okay, and there is an access IP over here, which is being governed by NTT Japan. There is another access ISP over here, which is being governed by Verizon USA. Okay, so all of these access ISPs, we have to connect them to form a global internet. One answer is we form a full mesh, something like that. Okay, obviously you guys are also come from the background of computer science. If asymptotically speaking, you must have studied the course of DSA or DA. Asymptotically speaking, the complexity of this sort of scenario is big O of n square. It's a quadratic complexity, right? कुछ याद आ रही चीजें? You guys are remembering some things. We calculate the complexity, right? So asymptotically speaking, yes, okay. Thank you for confirmation from the DL mode. Asymptotically speaking, it's a full mesh. A full mesh, n is the problem size, and in DSA and DA, we were interested in the problem size. When the problem grows much larger, what will be the complexity then? So asymptotically speaking, this sort of network won't scale. So what we need. We are taking a stepwise approach to the current structure of the internet. Please note, obviously this is wrong. We all know this is wrong. Okay, so what we do, we have a global ISP. Okay, we have a global ISP who says that I am a global ISP and I have a footprint over the entire world. Okay, I have core routers and my own private network deployed around the globe, and I control those networks, and I am the one who can provide all of you access ISPs and interconnection among each other. Okay, so one example of this global ISP is Google's private network. Google owned is its own private network all around the globe, which has core routers deployed and links or fiber transoceanic fibers being deployed by the own money of Google. So its own separate private network, although it's not a global entity, but huge organization, right? But if it is such a profitable business, because this global ISP will then start getting money. So there is a factor of economy as well. So they will start getting money for peering the access ISPs. So obviously, in a profitable business, we can always have multiple market players. Okay, and these market players will say that, okay, I have my own area in which I provide global connectivity to the access ISPs of my area, because having a very large global footprint for a single tier 1 ISP is very difficult. Okay, Google has it, but it's still very difficult. It's a very capex oriented thing. Capex stands for capital expenditure. You need to have a very large initial investment to have such sort of global footprint. So there can be multiple ISPs, tier 1 ISPs, who can say that, okay, we provide these things, we provide these things, but then those ISPs have to connect to each other. So then comes the concept of peering links. Okay, so these are the peering links. Sorry, I should use mouse. These are the peering links which connect to different tier 1 ISPs. And okay, right now again our global internet is being connected, but then a single link sometimes don't suffice. So we started to have a concept of internet exchange point, IXP. For example, there is a huge IXP in London. Okay, there is a huge IXP in Singapore. Okay, and Pakistan is being peered to different tier 1 ISPs with the help of the Singapore IXP. Okay, so we have 5 or 6 undersea cables. Obviously, all of them, starting from our gateway, Karachi, and then they peer to Singapore mostly, or Oman, or some other Middle East point, right? So the IXP is the one internet exchange point which basically provide a peering location to several different ISPs, which can be at tier 1 level or at tier 2 level as well. Inside, if we are talking about regional IXP, okay. But here this is something large. Okay, so just like a London IXP, you can read more about it. Regional networks are there, and then the CDN comes into play. So modern internet in the modern day internet, because the content is so overwhelming, and especially there is a very very large amount of content which is very popular. Okay, so and it is being requested by users, global users all around the world. So that sort of content is usually being delivered to the user with the help of CDNs, okay, content distribution networks, and then these CDNs also become a market player, become an entity in the internet structure. One example of CDN is Akamai. Have you heard of the name Akamai? Akamai, Limelight. Google is also a CDN. For instance, I gave you guys an example. If you guys are very old users of YouTube, I think all of us are very old. We might be using YouTube for more than 10 years, I think, right? So if you guys have noticed a very clear improvement in the quality of YouTube video streaming over the last 4 or 5 years as compared to when you used to use YouTube maybe a decade ago. Have you guys, itna yaad hai ki nahi? Can you correlate this example? YouTube shift to the CDN of Google somewhere around 4 or 5 years ago. I don't remember exactly the date, maybe in 2012, 2013, 2014, but it shifted to the CDN of Google. Now Google say, I am a content distribution network. I distribute content around the globe. You are YouTube. You have a very large content which the user around the globe access. And every time a user from Sydney, from Amsterdam, from Islamabad access your content, let's say it's a famous new song from I don't know, Taylor Swift, okay, or anyone else, okay. Every time someone wants to access, that song which hits the billion views, Gangnam Style, okay. Anyone wants to access a very popular video, the user come all the way from its source to the destination, which is the data center in California, in United States, and then take that content, and that content is being fetched. Why don't I bring the content near to your users? So the users from Islamabad will get that popular video from Singapore, and the users from Amsterdam will get that popular video from somewhere near, maybe Frankfurt or any other node. I have all the nodes. I have data centers placed over the globe. I'm a CDN. I'm a content distribution network. Okay, you give me your content and give me your money. I will put your content in my data centers and make sure that your users will not have to move 20-25 hops around the globe, but let's say after 2-3 hops they will get the content. So obviously the response of that content will be much fast for the user. For the user, it will be a very improved PLT, page load time, or the content load time, you can say. Okay, PLT is a very important performance measure in the WWW, World Wide Web. Okay, so every company over the internet, every organization would like to reduce its PLT, page load time, because reducing the PLT would mean a better user experience, and a better user experience would mean, you all know, right? Money. Okay, I mean hits to your websites, hits to your contents, and popularity, and all those things. So CDNs comes into the play, and there are multiple CDN providers, and the modern day internet structure could become something like that, in which we have tier 1 ISPs. Okay, over here, Verizon, entity, things like that. And even Google is also tier 1 ISP. As I said, it has its own private network. It has its own. And then we have content distribution network, Google, Akamai, Limelight, or many others. Okay, so for instance, multiple times if you visit a website, if you notice on the bar below, on the address bar, the addresses are changing very quickly. So these days, when you load a single web page, usually the content of that web page are being fetched from several servers. Okay, some of the content is static content. It is fetched by the actual actual main server of that particular website. For example, you go to www.coursera.com. So the main front index.html page is being fetched by the actual website, actual web server of Coursera. But then when you go to the content, maybe Coursera is getting services of Akamai or some other user. For example, Amazon uses Akamai's CDN, and similarly YouTube uses Google. So there are multiple market players, and these CDNs comes over here. Okay, comes over here. Then there are IXPs, regional ISPs, and access ISPs. So this is the structure of the modern day internet. G, question please. I'm really sorry. No, it's my mistake. G. G.
Excuse me, sir, we cannot hear a thing. Maybe your mic is muted.
G, yes, I was not on mute. Something, I think there was a disconnection in internet on my laptop. So मैं ऑडिबल हूँ दोबारा जी आप लोगों के लिए?
Yes, sir.
Yes, sir.
Yes,
ठीक
yes,
है.
sir.
अब लास्ट कपल ऑफ मिनट्स ये जो क्वेश्चन है कंक्लूड कर रहे हैं हम. ये आप थोड़ा सा नॉइज के साथ ही सुन लें. ठीक है. ओके. अगर अगर अभी
Okay,
आ
sir.
रही है. ठीक है. क्योंकि वो there is some sort of internet problem with the Wi-Fi. अच्छा जी, recording yes चल रही है अभी. ठीक है. So the question, I want to repeat the question. The question is that I gave example of YouTube using the CDN of Google, and your good name please? Ali Amjad. Okay, yeah, I remember you yesterday asking questions. Okay, Ali Amjad is asking that which content YouTube would like to host to Google, would like to give to Google to host in its CDN network, in its data center. Obviously, YouTube would like that only the important content is being hosted at the Google CDN, because the amount of content you are requesting the CDN to host, you are paying for it. Okay, so this is a separate topic, and we will touch this when we will discuss data center networking and CDNs along with that. So we will touch that. So obviously the very quick answer is that the popular content is the one which YouTube would like to host. If you notice very carefully, it is actually there is actually difference in speed. Let me again repeat the question for everyone. He is asking that there should be a difference in the speed when we are using YouTube for different videos. For example, popular content should be loaded more quickly, and some content is popular regionally. So, for instance, maybe there will be no one viewing Coke Studio songs in Gambia, for example, where our friend is from. Okay, but there will be many people viewing Coke Studio songs in India and Pakistan. So that content of YouTube will be hosted more close to the node to India and Pakistan. Any Google CDN node which is more close to India and Pakistan. And similarly, yes.
Sir, there is a request. Please accept.
Yes. What is the
Joining
request?
Aisha
Joining
Naeem.
request?
Yes, sir.
अच्छा जी, ठीक है. Joining request accepted जी. ठीक है. Accepted, but she
You can join now the call, but obviously we are just about to conclude. The short answer to your question is that popular content is being hosted, and if you notice very carefully, there should be a difference between a video which is demanded very less frequently. So if you ask for a, a French song of 50s, this is something which is demanded very less frequently. Maybe even a popular French song of modern day can be viewed by some of the viewers in Pakistan, India, but that particular content should take a bit more time. There should be a difference between streaming, but you have to look into it very carefully. Otherwise, if there is no difference, then that means that somehow YouTube is asking Google to host all of its content in each and every of Google's nodes, which is highly unlikely in my opinion. It's really expensive for YouTube as well. Okay. Any other questions from DL mode, from FTF mode? So this is the I'm showing you guys something which you don't want to see. You want to see this, the DL mode, guys. Okay. This is something which we have in today. This is the structure. Okay. And as you can see, the names I was saying, Sprint, AT&T, Verizon, and NTT Level 3. These are the tier 1 ISPs over here. And then we have content providers, YouTube, Google, Amazon. Google, Akamai, Limelight, and then there are regional and access ISPs. Okay. So any questions, kisi ka bhi? If there is no question, we stop over here, and I will skip the remaining slides of introduction chapter. There is a whole bunch of content, delay, loss, throughput we have discussed, and but there is some this layering thing. We are studying the layering throughout the course. So I mean, this is, you know that these are the layers, the names of the layers, and all those things. So I will upload this slide. This thing, okay, this encapsulation, how message is being encapsulated and different headers are attached. This I will discuss somewhere down the line during the course. This is an important slide. But other than that, all the things are very preliminary, and we will conclude our introduction chapter over here. Thank you. Dr. Asim has arrived, so let me stop recording. And attendance, there is no one on CMS. So